Alright, this one's a particularly gruesome one to do by hand. In order to find the Laplace transform, you would have to take the integral from 0 to infinity of f of t which is t cosine 2t e to the minus st dt. And the issue you run into is you have three things being multiplied together there. No easy way, no straightforward way to integrate that. What you would have to do to integrate, you have to integrate by parts. Let u equal t, du is dt. And then dv, of course, is everything left. And the bad news is, in order to integrate this, you'd have to use integration by parts again. Okay, so you would integrate that by parts, and that would be one of those ones that would cycle around on itself. And then when you get all done that, you're going to have to do the integral of v du, which means you're going to have to do yet another integration by parts. Particularly gruesome. We'll see a better way when we get to section 4.2. Alright, this one, I'm not sure I'm going to have space to write all this, but we'll try. So I take the Laplace transform, I get s, x of s, minus x at 0, but that's 0, plus 2 times y at s minus y at 0, that's 1, plus x of s equals 0. And again, I do the same thing here. I get s, x of s, minus y at s minus 1, plus, oops, I forgot an s there and there, because I'm taking transforms of derivatives, plus y at s, 0. So I would rewrite this. Grouping the x of s's together, I'm going to have s plus 1 x of s plus 2s y of s equals 2. So I distributed that through and then moved it to the other side. And I'm going to do the same thing down on bottom. I'm going to have s x of s. Then I've got plus minus s plus 1 y of s equals negative 1. Alright, now we're going to have to use Cramer's rule, and I'm really not going to have space. Let's see what we can do. We're going to have our D matrix is going to be our coefficients, s plus 1, 2s, s minus s plus 1, and our d sub x is going to have 2, negative 1 there, and then it'll have 2s and minus s plus 1 there. And finally our dy will have 2, negative 1 along the right, and s plus 1 and s. Okay, so to find x, we take the determinant of the d sub x matrix. That's going to be minus 2s plus 2 when I multiply that way, and then I subtract and multiply that way, plus 2s divided by, let's see, that's going to be, I got to multiply this way and do FOIL. That's minus s squared. Then I'm going to have a plus s and a minus s on the outside. Those are going to reduce out. Plus 1. And then I multiply diagonally the other way. That's minus 2s squared. So I end up with 2 over, doesn't look like a 2. 2 over minus 3s squared plus 1. I'm going to write that as minus 2/3 times 1 over s squared minus 1/3. So notice what I did. I pulled the 2 out, and then I pulled the minus 3 out. But when I pulled the minus 3 out, I need a 3 times s squared to get the 3s squared, but then I need a 3 times a negative 1/3 to get the plus 1 because I pulled out the minus 3. So I can do the inverse Laplace transform of that now. X of t is minus 2/3, and that fits into the hyperbolic sine form. So that's hyperbolic sine t over the square root of 1/3. Alright, you'd have to repeat to do the same thing for y. Find the determinant of dy, and then the determinant of d you already know, and then do the inverse Laplace transform. Okay, hope that helps with that one. Back to this problem again. This is almost the same problem we had back in section 4.1, except we had a 2 there instead of a k. What you're going to do on this one, you're going to notice that f at 0 happens to be 0. And we're going to take this f of t equals t cosine kt, and we're going to take the derivative. So the derivative is cosine kt minus t times sine of kt times k. Okay, notice that f prime at 0 equals 1. Then I'm going to take the second derivative, because I started with a t cosine kt, now I have a t sine kt. I'd like those to match. So I'm going to take my second derivative, f double prime is minus k sine kt minus k sine kt plus t times cosine kt times k squared. Now we use our rule that says the Laplace transform of the second derivative is it's s squared Laplace transform of the original function minus s f at 0 minus f prime at 0. But of course this one's 0, and that one there is just 1. So we're going to have the Laplace transform of this whole thing, which is Laplace transform of minus 2 k sine kt minus t k squared cosine kt is s squared, the Laplace transform of what we were looking for from the beginning, t cosine kt. And again, I'm going to run out of room here. These problems take space. Minus 1. Alright, so let me tell you, if I can just give you the general idea here. You're going to use the linearity properties of cosine, or of Laplace transform, I mean. So you're going to have negative 2k times the Laplace transform of sine kt, that's k over s squared plus k squared, minus k squared the Laplace transform of t cosine kt equals s squared Laplace transform of t cosine kt minus 1. Okay, so what you're going to do, you're going to move the minus 1 to the other side. You're going to move this to that side, which allows you to factor out the Laplace transform of t kt. Divide by the k squared plus s squared, and there you have your answer. Okay, hope that helps with that one. Okay, completing the square, we have s squared plus 6 minus 6s. Plus, we're going to have to add 9 plus 25, and we subtract 9. So we end up with, this is the inverse Laplace transform of 3s plus 5 over s minus 3 squared plus 16. Alright, now the deal is you got to make your things match. Since we have an s minus 3 here, we've got to have an s minus 3 up there. So I'm going to write this as inverse Laplace transform of 3 times s minus 3 plus 5. Now be careful here. I put a minus 3 inside my parentheses. 3 times minus 3 is minus 9. So I really did a minus 9, so I have to do a plus 9. Over s minus 3 squared plus 16. Alright, now we split this. This is Laplace transform inverse of 3 so there's my first piece, and then my second piece has 14 over the common denominator. Okay, the first one, this fits into one of our patterns. This one almost does, since we have a 16 on bottom. We really need to have a 4 on top. So I'm going to put a 4 on top, which means I need to put a 1/4 here, and then we're going to have to factor out that 14. So answer becomes, because of the s minus 3, we have an e to the 3t, and then that's cosine the 3 there, 3 cosine 4t, plus I've got a 14 over 4, that's 7 halves, and then I have the e to the 3t, and that one's a sine of 3t. Oops, sine of 4t I meant. Okay, this one. You said you weren't sure how to set up your partial fractions. The first one should have been an easy one. The bottom factor says s plus 5, s plus 2. Those are both linear, so you're just going to have linear on top, or constants on top. The second one, number 21, is kind of confusing. This s squared plus 2s plus 2, that's quadratic, which doesn't factor. So it's quadratic, that doesn't factor, that means I have to have linear on top. But since it's got the square there, that means it's repeated, so I need a repeat. So I need another linear on top. So that's how you're going to set that one up. Alright, this one. We have to use our theorem. So this is s squared capital X minus, it's going to be s times the original function, so that's 2s, minus the derivative, that's 3, plus, this one's going to be 6s x of s, minus 6 times 2 is 12, plus 25 capital X equals 0. Alright, putting all the x of s's together, we have x of s, and then I would have an s squared plus 6s plus 25 equals, putting all the things without s of x on the other side, looks like I have 2s plus 15. So that's going to be x of s is 2s plus 15 over s squared plus 6s plus 25. Now, unfortunately, once again, the denominator does not factor, so we have to complete the square. So that's going to be 2s plus 15 divided by s squared plus 6s plus 9 plus 16. So I had to do an add 9, which meant I had to do a subtract 9. 25 minus 9 is 16. So then it becomes very similar to a problem we did a little bit ago, where we have to make things match up properly because we have s plus 3 squared plus 16. So since I have that s plus 3 on bottom, I need s plus 3 on top. So that's going to be 2 times s plus 3 plus 15 minus 6. Again, same deal. The plus 3 is inside, so I did 2 times 3, which is 6. And then we're going to have s plus 3 squared plus 16. Splitting it up, that's 2 times s plus 3 over s plus 3 squared plus 16 plus 9 times 1 over s plus 3 squared plus 16. First one fits into a cosine pattern. Second one fits into a sine pattern if you multiply by a 4 and divide by a 4. Final answer, little x, is 2e to the negative 3t cosine 4t plus 9 fourths. I said fourths and wrote halves. 9 fourths. Ignore the red color, I suppose. E to the negative 3t sine 4t. Alright, this one, we're going to have s to the 4th, capital S. Then we're going to have minus s cubed times x at 0, which is 0, minus s squared times the derivative, which is 0, minus s times the second derivative, which is 0, minus the third derivative, which is 1, minus capital X equals 0. That gives us s to the 4th minus 1 times capital X of s equals 1. Alright, just realized I was going to get the wrong answer, and that's because I copied it down wrong. That was a plus, which makes that a plus, which makes that a plus. Alright, so getting the capital X all by itself, we have that. Now, if you look at problem number 26, it says inverse Laplace transform of 1 over s to the 4th plus 4a to the 4th. It gives a formula for that. So you're going to use that formula with, we need to get a 1 right here, which means we need a to be the 4th root of a quarter. Which is, if you want, the same as square root of a half. Okay, so you're going to use that formula, and you should get x of t is 1 over the square root of 2, and you're going to have a mixture here. This is an interesting formula. Hyperbolic cosine of t over the square root of 2 times regular sine t over the square root of 2 minus hyperbolic sine of t over the square root of 2 cosine, regular old cosine t over the square root of 2. Okay, well, I hope that answers all your questions. I skipped a few because they were similar to other problems we were doing. If you still have questions on those, let me know. I'll get back to you.